So let us look at the introduction to colligative properties. When we talk of colligative properties, these are physical properties of a dilute solution which depend on the number of non-volatile solute dissolved in the solution, but do not depend on the chemical nature of the solute particles. And all solutions containing non-volatile solute have certain properties in common. All these properties vary with the composition of the solutions in a similar way. And each of these properties can be measured over a range of concentration of the solution, and the results obtained depend on the total number of solute particles present in a fixed amount of solvent, and old for dilute solutions. So the physical properties, which is called the colligative, will always depend on the concentration of the solutions. The amount of the solute which is present in the solution will determine the magnitude of the colligative properties. Then these properties are called the colligative properties, and they are measured as the proportional to the number of particles in the solution. The greater the number of particles in the solution, the greater the extent to which the colligative property is affected. So when the number of particles in the solution is greater, the colligative properties will also be affected greatly. Then the colligative properties include a lowering of the vapor pressure of a solvent, elevation of boiling point, freezing point depression of the solution, osmotic pressure of the solution. Basically, we have the four colligative properties. Then when you look at the NB, so the colligative properties are important and useful for the determination of molecular masses for non-volatile solute. So we always use the colligative properties in order for us to determine the molecular mass of the non-volatile solute. Then we have the limitations of the colligative properties. These are principles under which the colligative properties may hold. Then we said that a correct value of relative molecular mass obtained by use of any colligative property is only obtained if solute does not associate or dissociate in solution. So we can only determine a fixed or a correct relative molecular mass of any solute particles using the colligative property. That is when the solute or that very substance does not associate or dissociate in solution. When the solute particles associate in solution, the number of particles in solution decreases, and therefore lowering the colligative property and increasing the relative molecular mass. So if the solute particles whose relative molecular mass is to be determined associate, that is coming together, several molecules coming together to form one bigger molecules, then it means that the number of particles in the solution will have to decrease, because after combining of this smaller solute particle which has been dissolved in the solution, they will become very few in the solution. So meaning that there shall be lowering of the colligative property and increasing the relative molecular mass. Then molecular mass obtained by colligative property for a solute that associates in solution is always twice the actual value. It's because of the combination of each of the molecule. The molecules come together to associate, they interact, forming a bigger molecules. Then when solute particles dissociate in solution, meaning the number of particles in solution increases, Now when the number of the particles in the solution increases, the colligative property also increases. This reduces the relative molecular mass. Molecular mass obtained by colligative property for a solute that dissociates in a solution is always lower than the actual value. Then another limitation or the principle under which the colligative property may work well is that the solution is supposed to be dilute. So the solution having the solute is supposed to be dilute. Then another one, there is no chemical reaction between the solute and the solvent. So the solute, which is supposed to be dissolved in the solvent, should not chemically react with the solvent, because when the solute react with the solvent, meaning that we shall obtain a new product. And remember, when we have reactants, the reactants combine to form new compounds, of which will be very different from the solid whose relative molecular mass is to be determined. Then the solute is non-volatile, so any solute that we are supposed to determine its molecular mass is supposed to be non-volatile, so it should not easily decompose on it or on exposure to any energy. Should really be very non-volatile. Then we're supposed to look at these colligative properties one by one. And when you look at the first one, vapor pressure lowering. The vapor pressure lowering of a liquid, this is the pressure exerted by the vapor when it is in equilibrium with the liquid at a given temperature. So that pressure which is exerted by the vapor when this vapor is in equilibrium with the liquid, it is what we call as vapor pressure lowering, and this one will always be at a given temperature. Then the vapor pressure of a solvent in solution is less than the vapor pressure of the pure solvent at the same temperature. This is because the non-volatile solid particles occupy some of the surface of the solution. Now when the surface of the solution has been covered or has been occupied, meaning that the tendency of the solvent to escape into the vapor phase becomes very low, because when the surface has been covered, then it means that the solvent in the solution does not easily escape into the vapor phase even if it is applied. So the amount of the solvent that will escape into the vapor phase becomes very low because the solute covers the surface of the solvent. Then the solution therefore has a lower vapor pressure than that would be exerted by the pure solvent. So for a pure solvent will always have higher vapor pressure because for it, the moment it is applied, it can easily evaporate, meaning that the amount of the vapor of a pure solvent into the vapor phase will always be very high because there is nothing that hinders it from evaporating. So the vapor will always be very high, meaning that for a solvent, it will always boil at a very low temperature. Then a solvent which is in a solution does not easily escape into the vapor phase because the surface of the solvent shall have been covered by the solute, which is non-volatile. So meaning a lot of it need to be put such that its vapor moves into the vapor phase. Then when you look at this sample question here, said explain why an aqueous solution of glucose has a lower vapor pressure than water at a given temperature. So for this case, glucose is going to be a non-volatile solute. It is our solute, and then water is a solvent. So now we said that we are supposed to explain why an aqueous solution of glucose has a lower vapor pressure than water at a given temperature. So water is a pure solvent, then the combination of glucose and water form a solution. So now always solution of glucose has a lower vapor pressure. The explanation is just the same with what we have said up there, because when water is mixed or it forms a solution with glucose, glucose being a non-volatile solute will always block, or it escape that is, it prevent the escaping tendency of the water into the vapor phase. Even if it is applied, water does not easily evaporate because the surface of the water shall have been covered by the glucose. Then for a pure water, there is nothing that hinders it from escaping into the vapor phase, and therefore, meaning that when it is applied or when temperature is applied, then it means that water can easily evaporate into the vapor phase because for it is pure and there is nothing that stop it from evaporating. So when you look at what we have written here, we've said glucose is a non-volatile solute, and when dissolved in water, glucose particles occupied some of the surface of the solution. So meaning that it occupies the surface of the water. This reduces the escaping tendency of the solvent particles into the vapor phase. Then the solution therefore has a lower vapor pressure than that would be exerted by a pure water. It is because water will always be pure and it doesn't have anything that prevents it from escaping into the vapor phase. Then for a solvent in solution, the vapor pressure lowering, that is, when we talk of vapor pressure lowering, that is a change in vapor pressure, a reduction in vapor pressure, which is the same as delta P, which is a delta P is a change in vapor pressure. This one is given by a formula as delta P, which is a vapor pressure lowering, is equal to the vapor pressure of the pure solvent minus the vapor pressure of the solution. So we always subtract the vapor pressure of the solution from that of the solvent. This is because the vapor which is being exerted by the solution, it is also still the same as the vapor exerted by the solvent, which is in the solution. Only that the vapor will always be low because the solvent does not easily escape from the solution, since the surface of the solution shall have been covered by the non-volatile solid which has been dissolved in the solution. So we said P naught solvent is the vapor pressure of the pure solvent. Then P solution is the vapor pressure of the solvent in the solution. Thank you.